Hello, everybody. Hello, everybody. Good afternoon, all of you. It's wonderful to see so many people here. Welcome to Imperial's annual Christmas lecture. And we're going to be seeing lots of really cool stuff later on. Mirko Kovac is going to talk about bio-inspired flying robots for future cities. And he's going to give a great presentation. I think it's wonderful that so many young people are interested in STEM, in science and technology and engineering and maths and medicine. It's so important nowadays that young people actually study those topics. My name is Simona Dyke. I'm Vice Provost Education at Imperial College, which means I'm sort of the head teacher here, I think you could say. So for all of you who come and study at Imperial, when you have the choice to go to university, I'll be in charge of your education and of your safety and your experience. And it's an absolutely wonderful job to be training so many young people for really great jobs in the future. And I was thinking, apart from saying that it's so wonderful that you're here and that Imperial is a great place to study, I would like to tell you a little bit about my own research background. I don't do a lot of research anymore because taking care of 17,000 students is pretty much a full-time job. But in the past, when I still did research, I was in public health. I'm a doctor by training, but I basically went straight into research after graduating from medical school. And public health is about health for large groups of people. So as a public health physician, you don't take care of patients anymore, but you wonder about what's best for large groups. And my subfield that I was studying was maternal and child health. So I was looking at the health of young children, but also children your age, adolescent health it's called. And one of the developments that was so important in the times when I was active as a researcher was the knowledge we were gaining around alcohol use. So I thought maybe I should tell you a little bit about that because it's a topic that I'm sure at some point you'll be quite familiar with. And I remember when my daughter was 13, she's now 26, so that's exactly 13 years ago. The knowledge, the wisdom at that time was that it was a really good idea for parents to let their children drink a little bit at home so that we become familiar with the feeling of alcohol. And I actually tried to make her drink breezers, which luckily she didn't like, so the experiment sort of failed. And then in the years after that, it became clear from really good research that it's actually really important for parents to give a better example than I was giving at that point. And that actually the more parents drink, the more children are likely to drink. So my son, who's 4 years younger and is actually in the audience right here, raise your hand, Daniel, he's right there. He raises it very carefully, but he's really sitting there. He didn't get that breezer experiment. I'm not sure he would have liked it, so it's actually probably good he didn't get that. And the reason why public health people and educators and physicians were at that point pushing for a more careful policy was that at the same time there were lots of people studying the development of brains, and they figured out that brains actually develop for quite a long time and that alcohol is also not very good for the developing brain. So I'm going to give you a little quiz. How long do you think the human brain is developing? Is it until the age of 19, until the age of 21, or until the age of about 23? Can I see hands for who thinks that the human brain stops developing around 19? Raise your hand. Not many hands. You're probably very good at taking quizzes. So what about 21? Who thinks brains stop developing at 21? Few more hands. Quite a few adult hands too. Probably wishful thinking. So who of you thinks that brains stop developing around 23? Great, you're very good. Maybe you've already read about this, and that's actually true. We think we know now from neuroscience and other really interesting fundamental research that human brains don't stop developing until about 24, actually 25. And we also know that alcohol, and especially binge drinking, but also alcohol drinking regularly, is really not good for a developing brain. So we know that young people, children who drink a lot of alcohol, actually make themselves less intelligent, make themselves less capable of studying, and that it really is a bad idea. And as the result of all this research, the alcohol laws in the Netherlands changed. That's where I'm from. And right now the drinking age is like in the UK, 18. But when I was doing my research, it was still 16. So that basically meant that 15-year-olds would try and drink. And that's really not a very good idea. And for me, it's such a wonderful example of how very fundamental research becomes applied and then becomes really important for everybody. And I think that's the message I want to give to you today. And then, of course, you should really listen to this wonderful speech, and I'll stop talking. Not all of you will actually become researchers, become scientists, but it's so important that you understand the importance of thinking academically, of understanding why research data are important and applying them to your life. So if you become a politician or a public health worker or someone in charge of a school, it's very important to know what scientists do and why science is such a fundamental part of our daily lives. And that's also the wonderful part of this presentation. The robotics, it's a very multidisciplinary field, so it means lots of different scientists work together, computer scientists, aeronautical engineers, mechanical engineers, and lots of other people. But it can also be very applied, and I just heard from Mirko that these robots that he'll be talking about soon are actually used for medicine delivery in Africa. So it's not just really great to be developing wonderful tools and interventions in the lab, but it becomes super important when they start being used in real life. And that's what Imperial is all about and what you're going to learn once you come and study here. So it's wonderful you're already getting a taste of this tonight. And again, welcome here. I'm really looking forward to the lecture. And now I'd like to introduce Annalisa Alexander and her son Seb. There they are. Annalisa is from Outreach at Imperial, and Seb is her 7-year-old son, and they're going to be introducing the lecture. So thank you very much. Have fun. Thank you.
Thank you, Simone. Thank you very much. Wow, so many of you. Thank you very much for coming here tonight. Are you all feeling a little bit festive? Yeah? Who said no? Who said no? Bah humbug, no. You can't help but feel festive. It's December. It's a lovely time of the year. Have you all been to the fringe events in the main hall, in the main entrance? Yeah? Oh, it's brilliant. It's science around the world tonight, so if you haven't had time, and if you're allowed to, afterwards, you must go and have a look at it. It's brilliant. A couple of housekeeping things before we kick off. There isn't a fire alarm scheduled for tonight, but if there is a fire alarm, you need to proceed to the fire exits, which are there and there, or behind you up the stairs, okay? Look around, familiarise yourself with a fire exit. We will help you out, don't worry. Actually, I'm sure we can probably get a drone and fly out of here, I reckon. I think we're all going to be fine. There's going to be some refreshments as well in the senior common room when this is over. So when we've finished in here, if you go out through the doors, and my colleagues will direct you to where the refreshments are. Mirko and his colleagues are going to have a stand there as well, so you can actually speak to them and hear about the work they do. There will not be drones to play with, I'm reliably informed, mostly because this one will want to play with them. So you can go and talk to them about all their wonderful work. Okay. As is the tradition with the Children's Christmas Lecture, I have here a child to introduce the lecture to you. Okay, are you ready for this? Do you know what? Bless him. We've been practicing really, really hard for this tonight, so give him a warm welcome. Okay. Right. Okay, there you go. Right, would you like to tell them what your name is and how old you are?
I'm called Seb and I'm 7 years old.
Oh, yeah, wow! Seven whole years old. Do we have anyone else here who's 7? We've got it. Now, really, 7 plus a bit. Oh, we have got another little 7-year-old. We've got a real 7-year-old there. I don't think you're 7. I'm sorry, look, I'm a scientist, I can tell. But we have got a real 7-year-old there. Hello, welcome 7-year-olds. All 7-year-olds and above are welcome. And there's a lot above 7 here tonight. So it's great to see so many of you there, whether or not you're 7. So we're in for an absolute treat tonight. Now, Sebi, you must really like science to want to do this.
Yes.
What do you want to ask the audience? We've got it written down, don't worry.
How many of you really like science?
Oh. You want to say that one, yeah.
How much do you really like science?
Yeah, how much? Wow! That is a lot of love. Wow! That is a lot of love for science. Well, you're in for an absolute treat tonight. We've got such an amazing lecture in store for you. What is this lecture all about, Sebi?
Tonight's lecture is all about robots. Robots are really cool.
They are, aren't they? They are really cool, yeah. Do you know what? I've got a robot in my lab that can dance and do Tai Chi. Yeah, beat that, yeah. Yeah, Tai Chi robot. I'll see your drones that save lives. No. What's special about these robots here tonight, Sebi?
They are special robots that fly like birds.
Wow, that is amazing. Well, I suppose we'd better get on then. So, Seb, this is your big moment. Are you ready? We have practice and practice and practice this. We've got it written down just in case. Bear with me. It's going to be fine. Off you go. I would like you now to introduce tonight's speaker. Are you ready?
Tonight's speaker is Mirko Kovac.
Yep.
And he works in our Aeronautics department. Let's give him a warm welcome, everybody.
Thank you very much.
Thank you. Okay, thank you very much. It's really the biggest, the best introduction I ever had. So applause again. Thank you. Okay, so also welcome from my side. It's my great pleasure to be here today and welcome you. And this talk is a lot about the past and also about the future. It is about the past because it talks about bio-inspired or biological systems. And biology, as you know, has a long history, has millions of years of time to develop what we see today. And it is also about the present because it is about the flying robots, and I will show some examples of things that we do in the laboratory, things that you can buy on the market today. And it is also about the future because these together can really create the next generation of flying robots. Now, you, of course, are the next generation, so I hope that some of the things that you see here you can take or can inspire you to take into your lives, into society in the future. Okay, so before I start talking about the technology, let me just show you one short video. Okay, so if you see that, I think there's something natural that happens in an engineer's mind. So if you want to build something, if you are a creator in nature, you see that, and the next thought is of how does it fly? How can I understand it? And then the thought afterwards is, how can I build something like that? And this happened a lot in many engineers, and this is how flight started, how they started to build large aircrafts, how flying robotics started. And it's often about trying to copy, first of all, to understand and then actually create these artificial living beings. And robotics is really a lot about that, about creating this artificial life, artificial beings. So this has started a long history, a lot with different applications. For example, here, pigeon post-delivery. So using pigeons, if you're not able to build them, you can use existing ones to deliver something for you. And that was a long time ago. Still used today, though. Then the next step was to do pigeon photography, so put big cameras on pigeons. So this was Second World War, where they used pigeons to take pictures of their enemies and so on. And then the next step is now that we can go to markets, to any shop, to Maplin or any other shop, and we can buy a flying robot that is able to take pictures. So we really replace now the pigeon with our robotic systems. So they can be used for a lot of different things, from military, drone surveillance, for example, to agriculture, so to identify where the weed is growing and then to inform where different nutrients are needed or water is needed. It can also be media, for example, doing aerial photography, so the BBC and many other companies use drones on a regular basis to do aerial photography and filming. Then also industry, so inspection, for example, looking at wind turbines or pipelines. to inspect them, and last but not least, also for playing with them or for having them for entertainment purposes. So can I just ask, who owns a drone, like a toy drone? Anyone? So a few people, about 20%, yeah? Do you like them? Somebody likes them? Yeah, okay, good. So I think they're quite exciting. You can buy them for a few £100 or even £30, I think the cheapest one. Now the next one up is the aerial photography. Does anyone own an aerial photography drone? Some? Oh, just a few, yeah. So that's about, yes. Okay, so they cost about £2,000 if you want a nice one. And does anyone own a military drone, maybe? Someone? Quite even more, yeah, okay. So they can go into the millions, of course, and much more expensive. So what I want to say here that these three different things are different classes. So they're completely different animals, different technology, different cost, different operation, different regulatory frameworks. So it's really two different things. So this talk is a lot about this smaller scale here, where actually the small scale enables a lot of applications that makes it affordable and can reduce the risk and the cost of day-to-day operations for a large part of society, not just the big, expensive government-type vehicles. Okay, so a few of them examples that are done today. So one is here in Gatwick Airport. They use drones to inspect the wings of aircrafts before they fly, so to inspect whether they have damage. And it's in fact, it is an EasyJet. And they do that together with Airbus and Intel. Actually, Intel is now developing drone. They bought a big drone company. And so they are doing this inspection, which makes it faster, cheaper, and much better than doing it manually, for example. Other examples include pipeline repair or pipeline inspection. So Shell and BP, for example, use that as well to inspect their pipelines and like this identify where the leak is and like this react better to different emergencies. Another aspect is drone surveying, where you can buy a drone off the shelf. So you can just go to a shop. This is SenseFly, the company that sells those drones. They can be launched by hand. They can fly, take a lot of pictures, and by stitching these pictures together, they can create three-dimensional maps of the environment. So they just fly above this, and then later can create this type of 3D maps. So this, of course, is very valuable for road planning, pipeline planning, or geological surveys, and so on. So this is basically today. So this technology you can go today to the shop and buy. The question is, what happens in future? So where does the field go, and where are the challenges as well? And one of the challenges is shown here. So you can fly, you take pictures, but once you reach another animal, they can be a bit jealous. And that's really one of the big challenges is how to operate, not just on a legal basis, but also so you don't endanger. So nature strikes back, yeah? Okay, the question is, where are we going? What happens in 20 years? What happens when you are my age? And so you're developing the system. So what kind of robots will we see in our everyday life, in our cities? And how can we get from today to this point? There are a few things that will happen in the next 20 years. One is that the planet will be very much a robot-enabled planet or even a robotic planet. So robotic technology is the fourth technological revolution, and it is already completely transforming how we operate things. So autonomous cars, robotic drones, robotic infrastructure that adapts to us, our buildings learn from our behaviors, our smartphone interact with the buildings, with the cars. So all this is the robotics technology and robotics revolution that is happening at the moment. We see a separate parallel trend on that, which is urbanization. So there are many more people will actually live in cities in the next 20 years. In fact, we'll have about 2 billion people more living in cities compared of today. So the cities will grow, they will become more integral, and much more people, even most people in 20 years will live in cities, and that's the prediction. So these people, of course, need a communication, they need to operate autonomously, like with they need to interact with each other, and we need to think of an ecosystem of systems, so systems of systems, or an ecosystem of robotic technology that will enable this. And if you think then what exactly is needed, I would like to emphasize 3 key areas today in this talk. Now, one is, of course, that all of them need to be around the human. They need to be human-centric and actually improve the well-being of the humans. If they actually endanger humans, I think it's the wrong technology to develop. So that's the first thing, like an ethics framework that we need to adhere to and develop together. The second, the first point, is on material flows, of how this type of technology can be used to enable logistics or materials flowing in the cities, because the city needs to breathe, it needs to have operate like a blood system where the materials flows. It needs to have the information flowing as well. Here, robotics can help and improve and provide the information needed. And it can also interact with the built environment, so with the infrastructure, with the buildings, with the architecture, to actually make the link to the building technologies and building systems of the future. Okay, so now if you think of the material flows and what are the needs of this type of cities. So we have transport, utilities, cargo, water. We need to contribute and move a lot of materials around in a city. In fact, in London alone, it is 360,000 tons every day that needs to move through London. So we have the tube system and so on. We have the road infrastructure. But what if, instead of having the roads, instead of having big lorries going from place to place, as we have at the moment, and what if you have a flexible logistics system that does it all in parallel? So instead of bringing one small packet from place to place to place, what if you have a parallel approach where we deliver everything at the same time? Now this can reduce the cost, reduce the time, and be much more cost-effective, environmentally friendly and so on. And so if you think then of this, let's see what is delivered. So Amazon, in fact, shows that about 80% or 85% of its packets that it delivers is less than 2 kilograms in weight. So mostly it is small objects that need to be delivered. And so you've seen, I'm sure, this kind of PR campaign of using delivery drones to deliver packages in cities. And this, of course, doing this in central London or in a city is very challenging because of the infrastructure and people and buildings and so on. So instead of going first to the city to deliver objects, it may be much more effective to develop it first in areas where there's much more space, where the delivery can be much more effective. And this is one project that I'm personally involved in, which is the Red Line project, that aims at creating a drone delivery network in rural Africa. So we are currently setting this up in Rwanda and testing blood delivery systems between hospitals. So part of this project includes also creating the drone ports. So Lord Norman Foster is actually creating the drone port and how the drone port can be a community hub at the same time where people live alongside with the robots and can also use 3D printing and interaction with the technology to educate the people there, but also to enable them to build their own drones and interact and use them for agriculture and a lot of different applications. So instead of going into building the road infrastructure, we can build the aerial logistics infrastructure. So the same happened with cell phone technology. So instead of putting wires into the floor, as we have in Europe, in Africa there's a huge trend of creating directly wireless infrastructure. So it can be a much more effective, much faster way how to do deliveries. Okay, now besides the delivery, of course, we need to know the information and have the information that goes along with it. So the intelligence needs to be part of the logistics system. And the question is, what kind of information do we need? Now, in a city environment, we need on one, for example, we need the traffic and people management, so we could have a drone that flies and detects where the traffic flows to optimize that. Or we could have energy management, where the drone flies around and detects the heat sinks in a city, so to reduce energy costs. Or also as emergency response in a tsunami or a nuclear accident, for example, the drones as well could go and sense the environment and like this identify where the danger zones are. And like this save the people more effectively. So the question then is, how can we do that? And what if we would have not static sensors that are deployed in the city, but we would have mobile sensor networks, that the sensors would be moving around the environment, attached to the building, sense what they need to sense, and even follow the different phenomena that they see in the city. So what if you would have the curiosity-driven nowcasting of the drones, that they would be like birds living in a symbiotic relationship with the city, with the people, and you wouldn't notice that the drones actually live above you. They would be self-reproducing, maybe they would be interacting with each other, recharging the solar cells by themselves, and so on. So this would make that the data is not just big, but also relevant, and it would just collect the information that is needed. So one research question, if you want to build that, is how to make these small sensor nodes move in the environment. How can we have something that actually moves in this complex terrain of a smart city or agriculture field? And so one example of that is small jumping robots, where we looked into putting swarms of jumping robots with small sensors that would be deployed in a city, and thousands of them would jump around and like this move effectively in the environment, following different phenomena, for example, heat sinks or pollution flumes, for example, and so on. So the robot we have built is this. So it's about 5 centimeters large and can take off. It has here a 4-bar leg system. It has a small motor, 4-stage gearbox, and a cam system. It's made of aluminum, so airplane aluminum, very lightweight. The whole robot weighs 7 grams only, and it can like this recharge and like this jump up very high into the sky. So important here, and this is what I want to emphasize on the biological inspiration, is that we really have to look at biology and only extract what is important from the biology. For example, if you look at the grasshopper, now the grasshopper might have these beautiful long legs to attract the male or the female grasshoppers, or it might have other behaviors, or the structure might be for other reasons, not just to be effective in jumping. So instead, we have to really look at that, extract the key design principles that make them jump, and then do creative techniques of engineering development to build this into engineering system, and then fabricate it to build the robot that we have. Like this, we have the effective jumping robot that is inspired from robots, but not just by copying it, but by going through the principles of what is underlying the mobility of the animal in this case. So we then have this jumping robot that we see here that would be able to jump, overcome relatively large obstacles, and like this mount stairs, which is something that you would never be able to do if you would have small like wheels or legs that would then actually be stuck in this. So the jumping actually really enables a lot of the different technologies. So wheels are really very limited, but we have here, see this, have you seen it? Oh, that's actually our lab pet. It's called la roue. Roue, in French means wheel, so because it has wheels. But it also, if you're nice to it, sometimes it likes it, so it comes, and then it can jump, and then it jumps. So that's why also we call it the kangaroo, And so it's actually, you can pet it afterwards. It's quite nice. But it really shows when it's flat, wheels are okay, but if there are big obstacles, then jumping can be really the big difference. Okay, now just to give another example how we combine this with flying, which is we look at jump gliding mobility. So we have here a jump glider that has the jumping legs, but then also wings that then allows it to jump off and glide down like this to descend, move in an environment. So for example, in a city, it could be deployed from an aircraft, attached to the walls of a building, then jump, glide down again, and like this move in the urban environment. We also look at different wing folding techniques from grasshoppers that can do this very effectively as well. Okay, going at the smaller scales, at the size of a real bee, which is about 2 centimeters large, there is a project that looks into this. It's called the RoboBee project, that develops the actual at-size robotic insects that fly in a similar way as the real bees. So here you don't see it very well, but here it is flying, and it can hover. And this is a 25 cents piece in the US. So it's very, very small, and it can flap at more than 100 times per second. So it's really the same techniques of the real bee and allows it to fly. The challenge here is still, so what is the challenge? You probably see it. Someone? Yeah? Yeah, it cannot fly for very long. Thank you very much. So in fact, it has here a cable that is connected to a power supply that allows it to fly. In fact, it cannot fly at all with battery on board at this size at the moment, I think. So instead, we can look then again into nature and look how insects fly. And in fact, they fly very effectively. And here we see one. So this is a butterfly that uses flap gliding mobility. So it flaps a little bit and glides. And by gliding, it can use also thermals and do soaring flights. So we use the thermals to fly up again and then glide down again. Like this, intermittently alternate propulsion with gliding flight. Now, this method could potentially be very useful for robots. So maybe we can build robots that have a propulsion phase and the gliding phase, and like this, they would be more energy efficient. Now, another thing that we looked at in parallel is this. So you know what that is, right? It's a rocket, I think it's from NASA, that takes off, and it uses rocket propulsion to be a very high-power propulsion system to actually boost it into the sky. So can we maybe combine the butterflies and the rockets in some way to create a rocket-propelled butterfly? So that was a quite nice idea we had, which we then built, of course. So this it is. It has here a small rocket thruster and small butterfly-inspired wing shapes that allow it to propel itself, then glide down, and then do the intermittent propulsion mode similar to the butterfly. So that was the initial thought we had. So to do that, we built these small rocket engines using multi-stage design and cutting them out of very heat-resistive materials using laser cutters and so on to fabricate this very precisely. And then we see that actually we can modulate the thrust. So the thrust is how much force it can apply over time. So we see that by changing the design of the combustion chamber, we can modulate the thrust that it produces, and we can create these thrust gliding phases using this type of techniques. So in some way, like small rocket engines on the robot insect. So the first test you see here, so the question being just, has it enough power to take off? And so by doing that, so it did have it, but just being the first test, it turned out rather dangerous. I didn't bring one actually here today for some reason, but so just the first video. Later tests actually were much more coherent. So you see one here that actually would be propelled and glide down and do this intermittent mobility much more effectively. So it's a lot about the platform design and the stability and calculations of when it is stable and when it is not stable. Okay, so let me share with you another example of the research that we do. And this is about how to completely cut off the energy, so save energy, by attaching to the environment, and like this, completely not use any energy because you are attached to the environment. For this, we can again look into nature. We can look into birds. They have this vision system, deep stall maneuvers, dynamic flight, together with their legs here to grasp to something, which is incredibly skillful how they do that, and it's very, very difficult to do something like this on a robot. There have been some work here at Stanford University doing small perching robots. So they get launched, then they have a sensor on board which allows them to pitch up and attach to the wall using small microspines on the surface. Amazing work. It's several hundred grams in weight, the platform. And so it's possible it needs a flight controller and sensors and so on. Now we also see that they really have this complex aerodynamics of the feathers that actually help them in doing this very effectively. So these are some of the things that we again can copy from the birds. But what happens now if you want to perch at a very small scale? Now if you want to build a robotic insect that does the same. Now, does a fly perch up in the same way as an eagle would do that? Does it fly, detect the wall, and then perch up with the wings and attach to it? Or not? So in fact, there are studies that show that it doesn't do this at all. In fact, it doesn't care about pitching up. It can't get bothered. It just flies directly into the surface, crashes into the surface, and then attaches by balancing or bouncing off with its legs. So it uses its mechanical structure as an impact protection mechanism to do the perching. So in a similar way, we've built this small microglider that is only 4.5 grams in weight and uses these small pins here, as you see, that snap forward when they're mechanically triggered from the surface to decelerate the aircraft and like this pinch into the surface. It bites into the surface. And so this in concept is similar to the fly because it doesn't decelerate. It's the impact, it's the mechanics, it's the mechanical intelligence that allows it to attach to the surface. Okay, another example of how small-scale perching systems work is this ballooning spiders. I don't know if you know ballooning spiders. Anyone has heard of ballooning spiders? Very few people. So it's called also the money spider. It's actually flying spiders. So if you don't like spiders, I'm sorry about this news. They're actually very small. They're not so dangerous, usually. No, I think they're actually not dangerous at all. But what they do is they spin their web, and by then using the wind, they use this as a parachute so they can glide long distances. So they do migration by doing this passive wind-supported gliding mobility. So that's quite interesting, actually. Quite interesting behavior is possible at several milligrams. Actually, they're very, very lightweight. So using a similar approach, we looked into ways how we can use string-based techniques to attach to surfaces, attach to structures, and exploit the adaptability of the string. So here the idea is that we have a robot that flies, deposits a string-based structure, a support scaffold in hard-to-access areas, and then a second robot that would fly and then perch to this and go up and down, similar to a spider, like this, not use any energy, and like this be able to stay aloft much longer at a very little energy cost. So also go into areas that you might not be able to do by just flying there. And so that's one of the approaches. Now, if we showed this on the larger platforms, but we also showed it at a very small one. So this one's the nano air vehicles, which are about 10 centimeters in size, so very small ones. And we show that these techniques can be used for these very small scales as well. So we need to, of course, think of the mechanical design of how to make the string, how to attach it. But we also need to think on the control system. So how do we control it? And here we have a control architecture that shows how this is done using force-compensated model-based controllers that then keep it balanced even though there's a string pulling on it and so on. So we need the technology, we need the engineering knowledge to do these type of things. But I think we also need the philosophy behind it. So besides the engineering, we need the biology that can actually support our way how we think about it. And so we have seen that at the larger scale, so if they're heavy and can carry a lot of sensors, we can do the complex perching. But when we get smaller in size, so less than 1 gram or 10 grams, we can use this bio-inspired mechanical intelligence that can actually enable it and make it much more effective. So this range of capabilities, I think, can really inform the next generation of robots. We can then also do things like that. So we can do weaving, weaving structures, so it makes its own spider webs, rest there, maybe capture some other animals or, capture other robots, and recharge as well. So build its own habitats in the environment, in the forests, in the cities. And that's the larger goal of this project. Okay, so we have one here, actually, that showcases some of this. So it's a small drone. It's a relatively large one. But here, again, the strings can be quite useful. Does it work? So if it's good moods, it can work. And so here we see a few things. So first of all, we see it uses a lot of energy to do that. So it's very, very energy hungry and can do this only about 15 minutes. We also see that the stability is not very good. So this is as good as it gets on an off-the-shelf system, but it's still moving around a bit. So there's still some challenge on keeping it steady. So this one has a camera. Right? Can we turn the camera maybe? And they can do filming, but again, needs to stabilize. So. Okay, thank you. Okay, so thank you very much. Isak, our safety pilot, thank you. So if you see a few things. So first of all, it's energy hungry. Second, it's hard to stabilize. And third, it's hard to fly, so it needs an expert user, more or less, to do it. And fourth is also, it is a bit scary, for example. So that's why we had to put the string on, so actually it wouldn't, go away. So the string and using these perching techniques, using strings actually might make it much more safe and overcome a lot of those challenges by attaching to the environment. Okay, great. So let me share you another example of some robots that we're working on. And this includes environmental water sampling. So what if the robots can not just fly like this one, but what if it can go into the water, underwater, move around and fly again, fly out, and like this move in air, on ground, in water at the same time? So that's really the goal, because most of the real world is not just a laboratory, it's not flat, it's not just air, it's really the multi-terrain capability is really needed for that. And the vision here is to create these aquatic micro-air vehicles, or aquamavs as we call them, that would be deployed. So it's a small kind of bird-size type of robots that get deployed by a rescue team in an oil spill response scenario, for example, as we see here. Then it would fold the wings, dive into the water, take a water sample or provide underwater video footage, and then fly out, open the wings again, and fly back to the base station. So here again, sounds a little bit like science fiction, right? But in fact, it is as well very difficult, because the aerodynamics, fluid mechanics involved in that is very different in air and in water. We need to think of impact protection here when it crashes. We need to have different control systems in two different fluids, different sensors, also different ways how to change the morphology to be effective in both fluids, and different propulsion systems as well of how to transition between the fluids. So there's a lot of engineering challenges that we need to solve to do that. We did this by looking at the flying squid. I don't know, you know squids, right? There are some species of squid that actually fly by jetting through the surface and keep on jetting, then they spread some soft wings and like this jump glide on the water surface. So is there something that we can learn from them to make a jet thruster that uses water jet, like a water rocket, to propel itself through the surface? And this is exactly what we have did. So we have this gas tank with 60 bars of pressure that then ejects the water out of its body, and like this would fly longer distances. Now to do that, we need to do a lot of math and modeling. So the mathematics and physics is really needed. So I just showed this, even though you probably haven't covered this yet in your school, I guess. But that's okay. It's actually very, very useful, because you can really understand how to build it. You can understand how it works. And it really is the key to making it work. And it also just has a beauty in itself. So mathematics really just simply has an elegance which is unmatched by other sciences as well. We can then use this to then predict the model, predict the design that we want to build. We can optimize this. We have to build a new valve system using shape memory alloy actuators and so on to enable this to create this high power thrust. And we can then see first lab experiments here where it is floating, so it's underwater, and then ejects the water in about 300 milliseconds and reaches about 13 meters per second flight speed, opens the wings and keeps on flying. So you can really transition from air to water to air. We did first tests in Croatia, excellent excuse to go to Croatia, to actually then see how it works in the field. So it folds the wings. By folding, the aerodynamics changes in a way that we can predict how it dives. It then transitions passively, again using buoyancy, while it is filling with the water, and then jets out itself again through the surface using just 1 degree of actuation. So the whole thing happens just by folding the wings and initiating the thrust of the thruster. So it does the whole procedure. Okay, so then if we compare this to the birds, we see that really we copied the wing folding, we copied the way how they move, but we can then also use the robots to understand the birds better. For example, we could use sensors on the wings to see how much load or how much impact is experienced on the wings while diving into the water. And this can then in turn inform biology, and would allow us to do things that we cannot do on a real bird. Of course, a real bird doesn't very much like to have sensors on itself. So instead of using birds, using animal experiments, we can use robot experiments. And this can be, again, a very ethical application and very improving a lot of the sciences, how it's done. Another example is here again, coming back to the rockets. You see I like rockets and combustion a lot. In fact, so I used to play with small firecrackers when I was a child. So now I still do very much the same, but it's much more useful here. And so what we do here is use calcium carbide, and if you put this into water, it actually creates acetylene gas. And by igniting this gas, we can create a combustion here that ejects the water, and like this would allow the thruster to eject and like this jump several times on the water surface. Here again, we need to do the modeling, but it allows us to use very little material to do, in this case, 10 launches. So it's a very fuel-effective way how to move and have sensors deployed in the oceans that would move by themselves, and detect pollution levels, for example, or pH levels. Also allow us to study climate change, for example, in the oceans. Okay, so the last topic, just to mention quickly, is the architecture. Now, how can robots help us to improve the built environment? So how can they make the link between the living, which is us, all of us, and the non-living, which is the buildings that are there to support us? So how can robots make this link? Now, what are the needs? So one is, of course, inspection. So that's the Battersea Power Station. So we need to inspect any kind of damages, for example. We need to repair them if we inspect the damage, we see them. But we can eventually also use robots to build and construct and manufacture the whole built environment. So this way of manufacturing we call aerial 3D printing, and it will allow us to build buildings by depositing material from the drone. So if you imagine the drone would fly and deposit materials while it flies, it would allow it to create different geometries, different architectures that are not possible to be built with, traditional brick and mortar type of approaches. Instead of having humans building it, the robots could do that much better, or much more complex geometries potentially. So then the challenge here is of how to do that and how to enable the robots to do this type of construction tasks. So the vision that we have here in this project that we have in the lab at the moment is to create swarms of flying robots that will go to a disaster zone and deposit material from the air and like this build shelter structures in those environments. So by doing that, it could actually save people in areas that are hard to access by other helpers or humans that would go there. So the robots can be the first responders and build the rescue shelters. Some examples of how this looks at the moment is this. So you see a flying robot. It deposits polyurethane foam and can like this build up different layers of materials. What we see here though is that the precision is really very difficult to get. It's very hard to control it very precisely. And this is one of the main challenges. So instead of using the robots, as you see, it still moves around pretty much, a few centimeters. So we developed this kind of stabilization extension here, which is a delta arm, which can balance the need of the robots. So if the robot still moves around because of wind or because of its instability or because of the drift of the sensors on board, it can use this structure here to compensate for that and still keep it very precisely hovering in one particular position. So doing that, actually, we can do this more high precision manufacturing. It's coughing, yeah? I don't know what it is. Okay, so using the similar approach, we looked into ways how we can use repairing, how we can use this type of robots to repair structures. And here the idea, which is something that we presented recently, is to have a robot that would go to pipeline leaks. So if you have a gas pipeline, for example, it would have a leak, for example. The robot could go and deposit precisely some repair materials to fix the pipeline leak much quicker than if we send a human to go there and actually do the repairs. So this type of application we see here, where we have the setup, so we have the foam, the gas coming out, and we have this delta arm to repair this structure. This is something that we have shown at the World Cup of Drones. So there is a World Cup of Drones. Happens every year in Dubai. It's in February. So last year we were fortunate to win the first prize on that with this application. So showing that actually can be used. And there is a lot of industrial impact of that and a lot of need because there are a lot of leakages that happen and endanger the environment. So having robots can actually help in that as well. Good. So the other case or another application is to preserve the heritage. So what if you have some very precious building or church? Can we use the robots to inspect that, repair that, and act on it in a way to protect it? So currently there's usually not enough funding to support and maintain our national heritage, so which is also our national identity. So how can we use robotic technology to actually preserve that? And one example is this, to fly inside of churches, fly inside of heritage buildings, to do these repair actions. One example we are doing at the moment is several of those churches, but also other protected heritage sites where we use the robots to inspect, but also repair these sites. Okay, another example is not the past, but also the future here again, which is the nuclear sector, the energy sector in general. So I'm not sure if you know about nuclear fusion, so you've heard of nuclear fission, which is nuclear reactors as they're in operation today. But the future, so the next 50 years, is devoted very much on the research side to nuclear fusion, which is, instead of separating atoms, is to fuse them together. And this creates a huge amount of energy. In fact, it creates about 100 times the temperature of the sun if you do that. And the sun actually also has nuclear fusion in itself. That's why it's so hot and bright. So there is a research center that works on that. It's in Culham, next to Oxford. And it has this nuclear fusion reactor that you see here. So it's a big donut shape. It has robots inside. And of course, robots make a lot of sense because it's very radioactive after operation. It's extremely hot. And because of this, it has these tiles of beryllium here, which is a toxic metal that shield this donut shape. So robots can be used to actually maintain that, repair that, and so act on that, so instead of sending humans there. So we did some trials there recently with the flying robots, or using them, seeing how they could operate in such an environment, whether they could be an alternative or even cooperate with ground-based robots, that we would have these systems of systems working together in cooperation, collaborate, and like this protect humans, or be an alternative to humans being there. So the question is, how do we make that a reality? Of course, we need the government to support that. We need the funding support as well. We need the regulatory frameworks. We need you as well as the future of our society to actually make this happen and develop that. And there are a lot of scope, a lot of space for ideas, and a lot of ways how you can contribute your creativity and ideas into this type of systems and build your own. We also can recognize that actually there's a huge market opportunity, and UAV companies, or these aerial robot startups, are some of the most successful with a huge growth rate. And this is because there is a natural need for growth. There is a need. It's not just a hype. It might be a bit hyped in the media, but there is a real need. And the big aerospace companies like Airbus or Boeing and so on were also the startups at some point. So the startups of today in this space will be the Boeings and Airbuses of tomorrow. We also can think of applications, and usually it makes a difference, or it helps in areas where your people that you would send in look like that. So you don't usually want people to look like that, because it's dangerous and endangers them, it's costly as well, and it's usually not very effective. So having robots instead or in addition can be very effective. The other application is urban resilience and recovery, so flooding response, nuclear disaster response, oil spill response, a lot of areas where you don't want to go or you need to go very quickly. And then instead of going manually, you can send the robots there to go first to identify what is needed, and like this save people more effectively. Last but not least, it can help in sustainable urban ecosystems where, as I said before, the robots would live by themselves in the cities, support humans, and like this being a symbiotic relationship with the humans in those environments. So be the friendly city drone that you see and actually supports you, provides information and data that you might need at that point to improve your life. So a few things that go into that we are here developing at Imperial College. One of them is a recent donation that we received from Bramal Vasudevan, who's an alumni from the college, who went away and came back giving a gift of 1.25 million to create this building, which is a new multi-terrain lab, which will be located here outside when you walk out of Exhibition Road. It's behind this building, so you probably walk through this court. It's Dalby Court. It's called Dalby Court. And at the moment, there is a construction site here on the right. You will see that. And this will be the new flight lab that we are building to develop some of those robots. It will be finished in July around, and ready for you to then as well do your testing if you want later on. So inside it will have water, air, ground, and really be an environment for testing these multi-terrain robots and looking at the interfaces of how they can not just fly far away and take pictures like we see today, but really interact with the environment, interact with humans, move underwater, move close to structures, repair, do repair actions, and so on. So this is really the next generation of robots that we're working on at the moment. We also have a larger initiative of the college in Imperial West, or the White City campus, which is in West London. So here is Notting Hill, Portobello Road, and here this entire area is the White City campus, where the college is building a large campus ecosystem for technology transfer. Also there we are building now capabilities and testing sites for the robots, including this Wormwood Scrubs Park where we can fly them outdoors. So all of this is the infrastructure or the platform that allows people to come in with their ideas and contribute to that. So if you then get this robotic planet, which is bound to happen, is in fact already happening, if we then recognize that it is in fact a human planet, and if we keep our values at the right place, doing ethical types of robots, I think then we create this smart planet that we're all looking for. So thank you for your attention.